Hello everyone. So today we're going to talk about the derivative rules. Okay, and so last time you saw that we were finding the derivative of a function at a point using the limit definition of the derivative, and we were also finding the derivative of a function using the limit definition of the derivative. So now using these rules, we're going to find the derivative of a function, but we don't have to use the limit definition to necessarily compute the derivative function. However, you still need to know the formal definition of the derivative. Alright, so don't forget the formal actual definition of the derivative, and absolutely do not forget the three equivalences that we had for the derivative. So remember, the derivative at a point A is the same as the slope of the tangent line at point A, which is the same as the instantaneous rate of change at point A. Okay, so all of those things are equivalent and mean the same thing. Okay. So here, my first derivative rule that I have is that if k is a constant function, then the derivative of a constant is just 0. Okay, and so that's what this tick mark notation here means. This means, the derivative of. Okay, so the tick mark there is telling me, okay, the derivative of my k is just 0, where k is just representing any constant function. So when you see a number, f of x equals some number, the derivative of that function is just going to be 0. Okay, here I'm telling you if you have the derivative of k times x, where k is a constant, then the derivative is just going to be, the derivative is just going to be k. Okay, and so an example here, you could have that the derivative, say your function is f of x equals 2x, then the derivative function is just going to be 2. Okay, because here you see that I have a little 2 here in front of the x, and so the derivative of 2x would just be 2. Okay. Now the power rule basically says that if n is any real number, then if I have x to a power, the derivative of x to the power is bring down the n and then copy my x term, and then the exponent is just going to be n minus 1. Okay, so here, this is what we call the power rule, and so an example would be if you have f of x equals x squared, then the derivative is just going to be 2x. Okay, because see how I brought down the 2 came in front, and then now the reason why I just have 2x is because it's really just 2 minus 1, and so then that means that my derivative here is just 2x. Okay, and so these are what we call more general rules. Alright, so if f and g are differentiable functions, meaning you can take the derivative of those functions, and k is a constant, then we have the following. So here I have that k times f of x, the derivative of that is just copy my constant k times the derivative of the function. And then rule 5 is saying that if I have the sum of two functions, or more generally the sum of functions, okay, it doesn't need to be just two functions. If I have the sum of functions, then the derivative of that is just the derivative of the first function plus the derivative of the second function, and then more generally, if I had more functions than just two, it would just be plus the derivative of the third function, and so on and so forth. Okay, and then the sixth one is just the same as rule 5, it's just with a minus. Alright, so if I have two functions being subtracted, the derivative of that is the derivative of the first function minus the derivative of the second. Okay, so this is going to make our life a lot easier in terms of computing derivatives of functions, because as you remember, we had to use that long limit definition of the derivative, and then from there, do a lot of algebraically, solving the limit, and then from there, it would give us, what the derivative function was. So now what I'm going to do is actually introduce you to what we call math proofs. And so I know you were introduced to this in geometry, but just believe me when I say the setup and the format of those things it just doesn't look as much like traditionally like what we call a math proof, okay? Because you had like a given and like a t-chart or something like that. And so here you'll actually see the power of it, the use of it, because before it was like really annoying and difficult to compute the derivative of a function using the limit definition. But now using, finding the proof and looking at the proof and using these rules is just going to make your life a lot easier. So now you like sort of see a need and understand that these rules are useful, and it's great that we have a proof for them so that we can just use these rules instead of using the limit definition of the derivative to compute derivative functions. So looking at this, I'm going to prove that if f of x is equal to k, where k is a constant, then the derivative is just 0. And so now at this point you might be like, okay, but how do you even like go about proving these things? Okay, so this is what mathematicians do. First, we just kind of write down what we know in terms of the derivative, and we know the definition of the derivative function, right? So before I even get to that, I'm just gonna sort of side note to you guys that I know that f of x is equal to k, but f of x plus h is also equal to k. Okay, since whatever my input is, so whatever my input is, the output will always be k. Okay, and so if you think of that in terms of like a real life example, if you have like f of x equals 2, right, your constant function 2, then, f of 1 is just going to be 2. F of 100 is just going to be 2. Okay, whatever you plug into that function, the answer is just always going to be 2. And so if you visually think about that, it's there you should see a horizontal line with the height of 2, and for all x values, you always get that your output value is 2. All right, so that's where this f of x plus h equals k is coming from. It doesn't matter that this looks like a weird expression for my input. It just, no matter what my input is for my function, my output's always going to be k. All right, and so now you'll see where this ties into the proof. But first, I'm just going to write down proof. And so we always start by saying like what we're given. This is the part where you remember the t-chart. But here, I'm given the fact that f of x is equal to k, where k is a constant function. Okay, so I'm going to suppose f of x is equal to k, where k is constant. Okay, and so now I'm going to write down the definition of the derivative. Okay, because ultimately what I want to figure out or prove essentially is that the derivative function is going to be 0. All right, and so to do that, I have to write down what even is the derivative function, like what's the definition, right? So we're just going to start with what we know, and what we know is the derivative function. The derivative definition. So here I'm going to say, okay, we know that f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. And so now this is what comes into play. What is f of x plus h and what is f of x? Well, we already know what f of x is. F of x is given in the problem in the beginning. It's k. Okay, and then I also noted to you before we even started the proof that f of x plus h is also k, right? Whatever I input into that function, my output's just going to be k. And so this means then that the limit as h approaches 0. Okay, now instead of writing f of x plus h, I'm going to write k in its place, minus, and then instead of writing f of x, I'm going to write k. Okay, so I'm just plugging in what f of x plus h is and plugging in what f of x is. And then this is all over 0. And so when I simplify this, though, k minus k is just 0, right? So this is the limit as h approaches 0 of 0 over h. And so 0 divided by a number is 0. And so I get that this limit is just 0. And so we say thus, the derivative is equal to 0. And we always put like a box at the end to end the proof. Okay, there's also some other things that people do to end the proof, but that's like more traditionally like what we do to end a proof in mathematics. We put a box at the end.